Can you see the slides and hear me?
I can hear you, and yeah, your slide is loading. Okay, so you can go ahead and start.
Okay, hello everyone. We are group 11. Today we're going to talk about the topological phase transition for 2D XY model. Here's our outline. First, we'll talk about the physical background for the XY model and introduce the features of the dataset. Then we'll present our proposals for this study. Next, we'll talk about the physical part first. The XY model is a lattice composed of several two-dimensional spins. That is, unlike only spin up and down in the easy model, the spins can rotate in a 2D plane. The Hamiltonian is a sum-over interaction of nearby spins in the system. A vortex is a key structure in XY model and expressed by the Widen number W. The plots on the right-hand side showed a group of nearby spins in the system. The position of the spins can be expressed by the polar coordinate r and theta. If the direction of spins rotate clockwise or counterclockwise, the direction of spin can be expressed by the formula W times theta plus a constant C. So when the Widen number W is equal to 1, we call the group of spins a vortex. And if W equal to -1, we call it an anti-vortex. To know why the XY model is important, we must introduce the Mermin-Wigner theorem. We know that the difference of the free energy is composed by two terms, the interaction minus the entropy term. When the spatial dimension is large, the interaction will be large too. So older phase can exist under a certain temperature. This corresponding to the Landau theory of phase transition. But when the spatial dimension is small, the fluctuation term will dominate, and there's no phase transition. About this, a theorem called the Mermin-Wigner theorem states that a 2D system with a continuous symmetry cannot be spontaneously broken. Therefore, since our 2D XY model is with a continuous symmetry, so there's no Landau phase transition according to the Mermin-Wigner theorem. However, a topological phase transition can still occur. We can derive that for lower temperature, the correlation between two spins will decay in parallel respect to their distance. This we call a quasi-order phase. But for higher temperature, the correlation will decay exponentially. We call it a disorder phase. The behavior of a vortex is different under the two kinds of phases. In general, the change of the free energy by creating a single vortex is written in this form. And we can determine the critical temperature TKT. So when the temperature is higher than TKT, and this is the disorder phase, the system will tend to generate more vortex, and vice versa. But when a set of vortex is bounded, the change of free energy should be written in the below formula. In this case, a bounded pair of vortex and anti-vortex can still exist under the critical temperature, since the sum of the Widen number cancels. So to summarize, when T smaller than TKT, only pair of vortex and anti-vortex can occur. And when T larger than TKT, free vortex can still exist. This is the end of the physical part.
Okay, I'm going to introduce the dataset and the proposal for the machine learning study. We generate the XY model spin configuration by the standard Metopolis algorithm. The system contains 32 squares of spin. We simulate 40 temperatures start from 0.1 and end by 2.5. Here is the configuration of low temperature and high temperature. The red color represents the vortex, and the blue color represents the anti-vortex. So you can see the vortex-anti-vortex pair appears in the low temperature configuration, which means that the number of free vortex equals to 0. But on the other hand, the free vortex creation can be accepted in high temperature. We can simply calculate the free vortex number for different temperatures. You can see that after T equals to 1, free vortex number higher than 1. This is one of the significant features of KT transition. Okay, next. Okay, once we have the spin configuration, we have the full information of this system, and we can simply compute the magnetization, energy, susceptibility, and heat capacity. And we can see that the critical point is near 1.1. Next. The spin-spin correlation behavior is the most important feature for KT transition. Here are the correlation function for low temperature and high temperature. Polar decay appears for low T data and exponential decay for high T data. Moreover, we can compute the correlation matrix. Ij elements represents the spin-spin correlation with distant Ij. Apply PCA to the correlation matrix for different configurations. We can see that high temperature data collapse on one single cluster and low temperature data collapse on the other curves. Then, next. We have 3 plans for the machine learning study. First, because we know the critical temperature for the system, labeling is not very difficult. With the high-level features which I mentioned just now, we can try the NM method to classify 2 different phases. Moreover, considering the spatial correlation, CNN may help us to classify the data. Next. We are more interested in discovering the phase transition. We believe that data for 2 different phases will be separated in latent space. Convolution VAE is a method that projects data on the latent space. After that, we can generate new data for XY model and obtain the observables by VAE. Next. And last, the diffusion maps method. Diffusion maps consider the transition probability between data and embeds data in a lower dimensional space. Distance between 2 data points is defined as their similarity of the probability paths. In the 2-dimensional XY model's case, data with the same Whiting number will form one cluster in the diffusion space. When temperature increases, data with the same Whiting number will form one cluster in diffusion space. When temperature increases, data will have more probability to transfer to other Whiting number. The dispersion of the data point within one cluster should be increased. We can capture the critical temperature by this property. Okay, the next page is our reference. Okay, this is the end of our presentation. Thank you.
Thanks. Very nice talk. So I'm lost a bit track of time. Okay. Any questions or comments?
So thank you for your talk. There are a lot of material. I kind of lost your talk since page 7. But I have a few questions and for several sides. So in page 3, I'm curious about the cartoon. I can understand Whiting number 1 is clockwise. For Whiting number -1, I don't understand your cartoon. Why it is anti-clockwise, and you have some arrow point to different directions.
Okay, so if we start as the first spin, can you see the mouse?
I can see your mouse, yeah.
Okay, so if we start with the spin and rotate it clockwise, we can see that the direction of the spin is rotate counterclockwise. So we call this case.
Oh, okay, now I got it. Yeah. Okay, I can see now. Thank you. And then for page 7, what is blue and red?
Okay, the blue is the anti-vortex, and the red represents the vortex. So you can see that in low temperature, there are 3 vortex pair. So the number of 3 vortex equals to 3.
I see. So you need to look for the location of vertex. It's some kind of some clustering need to be done, and you have definition of vertex with a different Whiting number, and red and blue represent where they happen.
Yes.
Okay. So in the middle means that you have a lot of vertex showing up. Okay. All right. And then what's the right hand side? It's a number of what?
Free vortex.
So is red and blue defines a free vertex?
Red and blue is a pair of vortex pair. So the free vortex is 0 because vortex we label it as 1 and anti-vortex we label it as -1.
So the number of the red minus number of blue, if the residual defines the number of free vertex. Is that right?
Yes.
Okay, got it. Yeah. Wow. So in the middle there, you probably have say 100 blue and 99 red, and then the difference is 1. Then number of free vertex is 1.
Yes.
Oh, okay. Interesting. I think the difficulty I have is after page 7 is there are huge materials in your slide. I think you guys did a very nice survey. It's just too much material for me to solve. And for example, if in page 9, you have a chance to explain what's the y-axis and x-axis. So this can help us to understand the figure.
Yes.
Just a suggestion for future, not for now. Yeah.
Okay.
Yeah.
So I also have a quick question. So it seems to me that the I don't know if it can be called order parameter or something, but it's the number of free vertices that tells us whether or not it's in one phase or the other, in the ordered or disordered phase. But when I look at your features of data set, I don't see number of vertices or something. I don't see number of vertices as well. Because this is not something we can measure experimentally. It has to infer from, say, specific heat or something. Could you explain why you choose this variable as your features of data set?
Oh, okay. Because when we look at the spin configuration, if there exists the vortex, the magnetization will not be 0.
Mm-hmm.
So we cannot measure it by experiment. The phase transition cannot be measured.
You mean we cannot directly tell how many vertices, like in reality, we cannot really tell how many free vertices in the system. So we need to infer from other variables like those in your features of data sets?
I think here I can calculate the free vortex because this is a model. But in reality, I think there is no experience measure the vortex.
Okay,
Yeah, I think just my view. Okay, so in experiment you are able to measure high-level features. You can measure magnetization, susceptibility, capacity, but you cannot do a individual spinner measurement. Yeah, and that also means it's not possible to do the vortex in construction directly at the microscopic scale.
Yes.
Okay, I see. Okay, thanks. All right, so if no other questions or comments, then we'll move on to group 12. We have Mr. Shen Yiting and Mr. Chen Zhenli. So one of you can start, share your screen.
Okay. Can you guys see my screen?
Yes.
Okay, so let's start. Hello, sorry. Okay, hello everyone. We are group 12. My name is Chen Zhenli and my teammate is Shen Yiting, and we are talking about the neutrino oscillation. Here's our outline. We will talk about the physics behind data and the data generation, and then the data description. Okay, so neutrino has 3 different flavors, which are electron, muon, and tauron neutrino. Each flavor neutrino is composed of 3 kinds of matrix eigenstates with certain proportion. We can describe such superposition in matrix form. Here we introduce the neutrino mixing matrix. It can be regarded as a 3D rotation, but we need to add one term, which is delta Cp, in order to describe the Cp violation. After simplification, we can get the so-called CKM matrix, which is describe the neutrino mixing, and it contains only 4 independent parameters. As neutrino propagates through a distance at certain energy levels, the possibility of one flavor neutrino transformed to another flavor can be expressed in this equation. The neutrino transition probability is related to the mass difference between 2 arbitrary mass eigenstates. Therefore, we will get the other 2 independent parameters, which are m²21 and m²31. Due to the unresolved mystery of the neutrino hierarchy problem, the m²31 can be either positive or negative. Note that for different sign of the m²31, we will get different transition probability due to the above relation. The chart on the upper right side is the current experimental measurements of these 6 parameters. Besides, we can do the charge parity transformation on the neutrino transition probability. The difference between the original and the Cp terms can be looked as Cp asymmetry expression, and we write down the A Cp. If A is 0, then that means the original and the Cp terms are the same, so Cp is invariance. Otherwise, if A is non-zero, then it will result in Cp violation. Since A has the complex part, so we can get the Cp condition for the parameter delta Cp as this equation. With these 6 oscillation parameters, we can use globes to generate the data we want. Globes is a software package for the simulation of long baseline neutrino oscillation experiments. First, we use Monte Carlo sampling to generate a bunch of input parameters data sets. For the left-hand side, we use Gauss distribution. And while the right side, we use the flat distribution. And the center value of the distribution is according to the current experimental data, which is here. And after we generate a million data sets of the 6 parameters, and we will input them into the simulator. And finally, we get the neutrino energy spectrum as our training data. And after preparing this data, we can start to do our machine learning. Okay, then Sengua, please continue.
Hello everyone, I am Shen Yiting. Now for data description. Here are 4 features.
I cannot hear you at all. Can you close to the microphone?
Can you hear me?
Slightly better. Is that the best volume you have?
Oh, sorry. Can you hear me clearly? Can you hear me?
You can
Let's continue
louder.
Yeah, you are still quite low. You need to be louder.
Okay. I try my best. Okay. Hello everyone, I'm Shen Yiting. Now for data description. Here are our features. We have total 1 million data. Each data contains 17 features. The first 6 terms are the energy spectrum of different flavor neutrino in different experiments. Here, DUNE and the T2HK are set by 2 experimental settings, such as the oscillation distance or the flux parameters, and they both use the same equation to generate neutrino spectrum. The middle terms are the 6 oscillation parameters, like theta. The last three terms are labels. It is the dual
So
spectrum.
may I clarify? Can you hear me?
Yes, I can hear you.
Okay, can you go back to the previous page? So when you say VE underscore dune, is that a single number or is a set of the number?
Oh, it's a set of number.
Array.
And it's an array, and the array length is 15. 50.
Okay, now I got it. Yeah. So then it's
Yes.
better if you go back to previous page. Yeah. So go back to previous page. So VE underscore dune is actually an array. No, you are going too far. So in general, it's nice if you can add the page number to your slide, then I can tell you which page I want to discuss. Yeah.
Yeah, sure. Okay, sorry
Fine.
about
But
that.
here VE dune is an array. VMu dune is also an array. Okay, with the 50 bins. Yeah.
Yes.
Right. Okay, good. Thank you.
Okay, Shenghua, please keep going.
Okay. It is the T2HK spectrum training data.
But this is just one event, right? You say you have 1 million sample, but this is just one of the sample, right?
Yes.
Yes, we just show one of them.
Yeah. So it's actually interesting if you can show 1 million data set into one graph. All you need to do is that, for example, you can show an average, right? So, and also the 1 sigma uncertainty band. So then we can see the overall average distribution of 1 million events.
Yes.
Yeah,
let's continue.
The three labels related to the occurrence of theta 23, CP violation, and the mass ordering. For now, we only try to train our model with CPB label. We will train our model by this way: SBM, decision tree, ANN, and DNN. For 1 to 3, pick 10,000 data to train. For DNN, we will use generator method to train. For training data, we combine 4 spectrum as input. Like B4, there are total 122 bins. We train our model like class week 6 and only take CPB label. Here is SBM model. Here is decision tree. The result is precise. ANN is the worst model which we train. It might be because that the dense is not deep enough. We haven't overcome DNN. We will try the API function later. Here are our reference. Thanks for your listening.
Thanks. Any further questions or comments?
Okay, so can you go to your mixing matrix slide, page 4?
Okay.
Are you sure this is a CKM matrix?
Yes.
Okay.
Because it contains the delta CP terms.
So have you heard of a PMNS matrix? What's the difference between MNS versus CKM?
I forgot that, but
Right. So it's a question hopefully you can answer in the final presentation. In general, there's a difference of the matrix between the lepton mixing and quark mixing. In the quark mixing, people call CKM matrix, but lepton mixing is quite complicated, and you are working on lepton matrix. So it'd be nice you can address my questions in the final report, all right?
Okay.
Okay, and then if you go to this ACP slide. That is page, okay, page 7. Page
You
7,
mean
yeah.
this?
Yeah, okay. So we know nature is a real number, but your formula is imaginary part. So I'm so confused. How can we measure imaginary number in nature?
I think this equation is right down in the CP phase. So it is just a expression to show whether our system has CP violation or not. But in fact, we are measuring the probability, I think.
But your HCP defined as a probability difference. So your first line is a two real number subtraction. Probability of alpha type neutrino oscillate to beta type neutrino minus probability of anti-alpha type neutrino oscillate to anti-beta type neutrino. These two are real number.
Yes. And
so why real number difference become an imaginary number in the second equation? I'm
because
confused.
remember the previous page for our transition probability, it really in fact it contains the imaginary part. So after we do the CP transformation and we minus them, then we will get the rest is the imaginary part. And I think the basic meaning of the imaginary part is not will not affect our delta CP expression, because we only transform these results to see whether it has the CP violation or not.
No. So a long story short, how come real probability equals to an imaginary number? I don't understand. Could you help to clarify the math? Then maybe help to explain this in the final report.
Okay.
A real number cannot be proportional to an imaginary number. Yeah. You say proportional to exponential I delta CP. I don't understand. How can a real number become an imaginary number?
Oh, the imaginary. I think the equation here is called the imaginary part. So in fact, is this imaginary number? I'm not sure.
No. You say proportional to exponential I delta. Exponential I delta is a complex number.
Sorry. I should not include the imaginary part here as our proportional, because I say that because our mixing matrix here is our mixing matrix, right? And in the middle term we have the exponential I delta CP terms. So that's why I say it is related to the complex part. So if the delta CP is 0, it will reduce to the traditional 3D rotation, and there is no CP violation.
Yeah, but no, what you say here makes sense, but I just don't understand this slide. Why is proportional to exponential? But let's not argue with this. Hopefully you can clarify this in the final report. Yeah?
Okay, so I think I should not use the proportion.
Okay, and page 8, you claim delta CP is flat, but it's not flat at all. Look at your delta CP, you have a spike at 0.
Yes, because in delta CP is our label, right? And when delta CP is 0 or 180, and we will call it the CP invariance. And while delta CP is non-zero or pi, we will call it the CP violation. So in our 1 million training data, we just divide them to two parts. One part is for the CP invariance, and the other part is a flat distribution to describe the CP violation.
I see. So the flat here means when delta CP is non-zero, is a flat. Okay.
Yes.
Right. So finally, in page 13, Is that true? In total, you have 8 class.
Oh, you mean if we do the multi-labels?
Well, in total, you have your M0 define inverted, non-inverted.
Yes.
Octane is just theta 23 greater than 45 or less than 45 degree. And
Yes.
CP violation is 0 or 1, right? So in total, you have 8 types, right?
8 types.
Yeah. M0 is 2, octane is 2, CP violation is 2, 2 times 2 times 2 is 8.
Yeah, that makes sense, yes.
So you should do a classifier. So I'm confused by your proposal. Why do you study 2 classifier for the rest? So for example, if I want to study CPV equal to 1 or 0, if I want to define it as a binary study, I need to choose. I only use the sample M0 equal to 1, octane equal to 1 to do this study. Or M0 equal to -1, octane equal to -1, and then to do the CPV study. So if you just split your 1 million sample based on CPV equal to 1 or 0, and then just do this clarification, this number will be broken because your M0 octane will affect the distribution. So
Yes, I
either
see,
you do the add classifier, or you need to do a study by fixing the M0 and octane value, and before you do the CPV classification. Right?
Yes, so you means the mass ordering may also affect the CP violation term.
So that's why I suggest you should make a plot, okay? And so it's a beautiful plot you show in the energy spectrum, but you only show one event, right? But what you want to do is that you should split all your sample into 8 class, and in each of the class, you should show the average distribution of the energy spectrum. Then you can compare those 8. You can get the first idea how different type of the M0 octane CPV combination affect your energy spectrum distribution. Okay.
Okay.
Yeah. Yeah, I have no more comments. This is a very interesting physics.
All right, thanks. So I think we need to move on to the next group from Mr. Hu Yingqi and Mr. Xu Weiqi. So one of you can start share your screen and go ahead. I think I can see your screen. I could see your screen before. I think you need to move on to that particular screen and share with us. I cannot hear you. I think you're talking, but it's very difficult to hear what you said clearly.
Is Xu Weiqi online?
Yes, I'm here, but
Okay, so I can hear
the second part.
Yeah, I can hear you. I cannot hear Hu Yingqi.
We can wait, hang on. You need to switch back to your slides. Yeah, we can see your slides and you can share. You can make a full screen, but still we cannot hear you. So maybe Xu Weiqi, you need to step out to do the presentation because we cannot hear Yingqi.
Okay. And
Well, we can also
so,
yeah.
Sorry.
Maybe we can move on to the next talk, right? And then Hu Yingqi, can you make effort try to find your audio? And you have a few more minutes to try to figure it out. Okay, so let's give them more time, and let's do the next group first. Yeah.
Okay. Okay. So we switch the order. So we move to group 14 first, and I think it's Yanting. You're going to make the presentation.
Yes. Can you hear me?
Yes, we can hear you.
Okay.
And you need to share your screen.
Okay. Can you see my screen?
Yes.
Okay. Then I will start the presentation. So hello everyone, my name is Zhou Yanting, and today I'll be presenting on the topic of electron showers. Here's the presentation outline. First, I will introduce the physics of electron showers, followed by the experiment setup, then data structure, and so on. So at the Large Hadron Collider at CERN, proton-proton collisions produce a large number of hadrons along the beam collision axis. These hadrons will then decay into many high-energy neutrinos of all flavors. This dataset specifically is on muons and electrons. And Phaser aims to break the record of the highest energy recorded for the detection of these neutrinos, and the range of neutrinos that can be detected is a few hundred GeV to a few TeV. And this is the experiment setup. So this is the phaser detector at the LHC, and it is located along the beam collection axis line, 480 meters away from the Atlas interaction point 1. And the emulsion film setup that is used in this experiment dataset is this part in front of the phaser. It's the phaser knee emulsion film setup. And here's a quick recap of what are emulsion films. Each emulsion film is composed of 2 emulsion layers and a plastic layer sandwiched in between. Then tungsten plates are interleaved between each layer. The base tracks are generated by tracking each point of entrance and departure in the 2 emulsion layers and connecting them to form a line. There are a total of 1,000 films in phaser knee, and the spatial resolution of these films can be down to 15 nanometers, with the density of the channels on the order of 10 to the power of 14 particles every cubic centimeter. On the right, you can see a conceptual design of how each flavor of neutrinos might interact with the layers. So here is a neutrino muon event generated by Genie. The length is 200 films long. The top picture is a side view, and the bottom one is a tilted view seen from the end of the shower here towards the beginning here. So you can see that there is a cone-shaped structure generated by the divergence of the base tracks. And at some point, the cone will reach a maximum number of base tracks in a single film, and this will be the shower maximum. And at the end here, you can see the base tracks shooting out in all directions as the muons interact with the film in more chaotic ways. Next, we move on to look at the provided dataset. There are a total of 20,000 shower events. The number of layers is only 100, indicating that there are 100 emulsion films. Each film records the number of base tracks there are in the film, and this makes up the dataset of base tracks. Label records the type of event by zeros and ones. 0 is electron and muon is 1. Next are high-dimensional features that can be calculated from base tracks. First is the number of base tracks at the shower maximum layer, then the layer index that the shower max occurred, and finally, the total number of base tracks in all 100 layers. The last feature is truth energy. By looking at the reference material, while it is possible to estimate the energy of the shower event from the base track data, you would need more information and features, such as the slopes of the base tracks, the position of each base tracks in the film, and so on. And only after combining all this, then you can estimate the shower energy. So this is impossible to do with just this dataset, in my opinion. So when training, I treat this truth energy feature more like a low-dimensional feature rather than a high-dimensional one. So next, we move on to data visualization. The energy in the dataset has no unit, but judging by the fact that the maximum energy allowed in phaser is on the scale of TeV, and the maximum number is in the millions, the unit is likely MeV. We can see that in this dataset, there are quite a number of low energy events, especially for muons, and we will look into them later. Here is the visualization of the number of electron and muon base tracks in each layer. For the electrons, you can see a steadily rising curve for many showers, indicating that the shower cone is continually expanding. There are also some showers that are shaped more like muon events in the right, over here in the bottom, with a bell shape and shower maximum in the earlier layers. For the electrons, I found out that these curves are mostly, increasing curves are mostly created by high energy showers. And these over here are mostly created by low energy showers. This will be discussed later. So here's a histogram of the layer index of the shower maximum of each event. You can see most of the electron events have a maximum at the last few layers, indicating that the shower is continuously interacting with the films to create more base tracks. The muons, however, have a maximum spread out along the 0th to 50th layer, indicating that many muons just pass through the films without causing interactions. Next is the number of base tracks at the shower max layer. Again, there is an obvious difference in the number, but curiously, there are quite a number of events with a very low number of base tracks, especially for muons. Since they contribute a lot in the dataset, they can cause some issues when training the classification model. Next, we dive deeper into the base tracks dataset. Using the information from the previous high-dimensional features, we can split the data by the position of the shower maximum and get the energies to see what energy level of shower event contributes to these different base tracks. So here we have split the base tracks by position of the shower max at 90 for this is electrons. And we can see that this is quite a good split. And we find that the steady inclining curves are mostly contributed by high energy ones. And the events that don't have shower maximum at the end are low energy events. But it should be noticed that there are still low energy events that can still have the shower maximum at the end. For muons, however, it is not very distinct, as all energies have high and low curves, and the only feature that can be interpreted is that most of the high energy events have shower maximum at deeper film layers. So why do the muon events have base tracks like that? The base tracks of muons are not like cone-shaped, as we can see here. Instead, they have explosions of base tracks, and the particles quickly get stopped in the material, so that all muon base tracks have a bell-shaped curve. This is 1,000 layers of film, while only our dataset only has 100 layers. So the dataset might only have gotten the first explosion, or else there would have been multiple peaks in the curve. Finally, we look at the total number of base
I think
tracks.
you need to wrap up in the next minute or so. You still need to talk about your proposal, right? So
okay. Then I will just skip to the proposal. So this is the model training that we use. We try to use CNN to do the classification for this dataset. The reason is that while many features seem like it is easy to distinguish electrons and muons, due to the sheer number of low energy events, it may cause problems because low energy events of muons and electrons have similar features. So we hope that the CNN will be able to combine these different features and perform an accurate classification. We have actually tried it already, and we do not show here, but we found out that using high-level features and shower energy to train the model did not give very good results. The accuracy is only around 60 to 70. We then changed to directly using the low-level feature, which is base tracks, to train the model, and this gave very good results, which I show here. And so we have two dense layers, and this is the loss function binary cross entropy. We use Adam for the optimizer, and the training data vs test data is 90% of the total data set vs 10%. And here's a quick glance of the model training results. And you can see that we have a very good accuracy and a very fast decline in loss and very good true positive rates. And this is the reference, and this concludes my presentation. Thank you.
Thanks a lot. Any questions or comments?
Okay, so can you hear me?
Yes, I can hear you.
Yeah, sorry, I lost in the middle. Just be sure. So two of you are sitting in front of one computer, do the group presentation. Is that right?
I don't think the other teammate is here. Yesterday we had a meeting and he said that he has some issues and cannot finish his part. So almost all of this is made myself.
Okay, we can discuss this offline.
Yes.
So just for your talk and page 16, can you clarify what exactly the problem you try to solve? Are you trying to do the classification or you are trying to do energy regression?
I'm trying to do classification of the muon and electrons.
You want to classify electron from muon. Okay, got it.
Yes.
And also your model, I don't understand your model. You have a 2 dense layer, but in the title you say you want to do CNN. But I don't see any CNN layer in your page 16. I'm confused. And usually we want to have some hidden layer, but you only have an input layer and output layer.
Okay, I may have gotten confused with the name of this type of model, or
and I don't see CNN layer at all in your summary table. So this is just a thing I want to point out. Okay.
Oh, okay. I will revise the model that we use.
So in general, if you guys have a issue or problem to train the model or to define the project, you should feel free to talk to TA. And we have a working hour time, right? For example, this afternoon or just later, yeah? It's good to discuss with TA, yeah.
Okay. Thank you.
Okay, thanks. So I think we can move back to group 13. Sorry. Sorry, let me. Oh, shoot. Sorry, I need to switch up. Okay. So group 13 could Inchi try again to speak us, see we can hear. Okay, oh, it's Weiqi who is sharing. Okay, we can.
Yeah.
We can see your screen.
Inchi and me are here, so can everyone hear us?
Ah, great. Yes.
Yes. And the first part is about Inchi, so I would like to let Inchi start his presentation. So Inchi, please start your presentation.
Okay, so we are group 13, and I'm Hu Inchi, and my teammate is Xu Weiji. Our topic is YSO classification with IRO sky data. So for data description, we have 3 data source. The first is OWISE, the second is 2MASS, the third is UKIT. And we have 7 bands wavelengths observation for JHK W1 to W4. And we have, for the label, we have 3 labels. The first label is main sequence star, the second label is extragalactic object, and third label is young stellar object. And we have 2 kinds of feature. The first kind is photometric data. We have 28 features. And the second kind is the image data, the original image data. So for the original image data, we have 4 band wavelengths, and for each image, we have 300 pixel by 300 pixel. Okay, next. So for the observation and photometry, first we have 2 systems of waveband. The first system is WISE. So in WISE, we have W1 to W4. It's between 3 micron to 22 micron. And then for the second system is 2MASS system. In 2MASS system, we have JHK band, and it's between 1 micron to 2 micron. And then for the photometry process, first we have the image data of each of W1 to W4 band, and then we use the point spread function and do the profile fitting photometry and the aperture photometry. And then finally, we get the photometric data. So the image data is low-level data, and the photometric data is high-level data. Next. So for the star formation and YSO classification, so as in Professor Dawei's speech, we can know that the YSO can separate it into 4 classes, class 0 to class 3. And then the left-hand side is the spectral energy distribution of each class. So in the red circle, we can see that there are the red circle is the component that dominate by the disk structure and the envelope of the YSO. So it is hard to identify the YSO by only see the spectral energy distribution. So why can we classify YSO? In traditionally, first method is the spectral energy is the spectroscopic. So in spectroscopic, we use the molecular emission line to identify the YSO. And the second method is the multidimensional magnitude space. So in multidimensional magnitude space, we use the spectroscopy result and plot the spectroscopic result in the multidimensional magnitude space, and then find the boundary of the YSO of the multidimensional magnitude space. And then in that region, we consider that the object in that region are all YSO. Okay, next. So, but why we want to find the more YSO is because if we find the more accurate and more YSO, we can calculate the star formation rate in the galaxy region correctly, so that we can know more about the star formation rate and gas surface density relation in the galactic region. And then it is important to know this relation because it is important to know the mechanism of star formation in the interstellar medium. Okay, so the data part is for the Xu Weiji.
Okay, I would like to show the data structure. Firstly, we can focus on the imbalanced data. I plot the ratio of each label. We can see the star has contribute almost 98% to all data. Sorry. And
sorry, it's actually mute. Yeah, go ahead. Actually mute. Sorry about that.
Okay. And we can see the star contributes almost 98% to the world data. So this data is imbalanced. And this slide, I show the correlation matrix of each class. And correlation matrix has another usage for the further research. So I would like to skip this slide. And this part is about the scattering plot. We can see the 3 kinds of the object, galaxy, star, and YSOs are highly overlapped to the wave base, and the plot is pick up 2 features from the 7 features, just like the W1 visit as W2, and this is the 6x6 plot because we pick up the 2 features from the all 7 features. And this is about the distribution plot. We can see the star's behavior as well as the total because the star contribute almost 98% to all data. But actually, we can see the galaxy and the YSOs has a different behavior. So even they just contribute 2% to the total data. And in this slide, I plot a cartoon to show our procedure. The first part is about the data preparation because our data is imbalanced. And the green box is about a machine. We have to choose we have to pick up a best machine, a best model to train our data, and it will give us some result, and we will comparison each result from the different model, and then change some strategy to dealing with the data, and then train the machine again. In this slide, just show the detail of the data preparation, and almost 30 we use a scikit-learn package, sampling package to deal with the data. And the main challenge I would like to conclude, our target is to find a best pair of the sampling method and the model to give us a best performance classifier. So the first challenge is use the sampling method, pick up a sampling method. We have oversampling method, undersampling, and the combination both. And model, we decide to use the decision tree family and their advanced version. And the final task is to have a objective judgment of the performance from each model. We have to design a way to give each model a scores and measure their performance. So this slide is our main task. And I would like to stop here, and next is the reference. Okay, thanks. And any question?
Thanks. Any questions or comments?
Yeah. I'm wondering page 3. So you comment on low level and high level, but what exactly being computed as a high level feature?
You mean
the right hand side, yeah. You say
yes.
It's a low level, and then you eventually have a high level feature. So what is the high level feature calculated from the low level feature?
The result got from the low level feature is the magnitude of the star and the chi-square and signal to noise ratio from the photometry. So we get 4 data from each band. So in total, we have 28 features.
And 28 feature is calculated from the image?
Yes.
But in previous page, okay, if I understand correctly, you have a 28 photometry data.
Yes.
These are computed from the image, the pixel image, right? Okay. All right. So in page 4, the right-hand side, you have a red, green, blue, 3-dimensional plot. What are the XYZ axes?
Oh, the XYZ axis is the magnitude. And
so it's 3 out of the 28 feature in describing page 2. Is that right?
Yes.
So because it's not visible, so which 3 are plotted? So in page 2, you define 28 features. So which 3 are used to make the plot in page 4?
It's for W1, W2, and W3.
W1, W2, W3. Okay, got it. Okay. And now in page 5, the XY axis. So are they computed from your 28 features? I don't understand how to relate the 2 axes to your features.
Oh, it's the picture from the other paper.
So this has nothing to do with your study. I can't understand some SFR and some gas. How to calculate these two variables?
Okay, so if we found more YSO, we can do more accurate calculate of some SFR. And then we can get the more accurate relation between some SFR and some gas.
So you are able to compute some SFR from your feature?
Yes.
And it's one of your goals. Did you make this
Yes.
plot by yourself? In page 5?
No, it's from the previous paper. It's from the other paper.
And then what's the relation for your study? You want to remake this plot or what? You want to cross-check this plot? What's the purpose of page 5?
Oh, so for the previous paper, they don't count. They don't calculate the SFR correctly. But I just wondering that if we use machine learning method to find the YSO and calculate SFR, what the result will we get?
So you want to develop a machine learning, identify YSO,
Yes.
and then recompute this graph. Is that right?
Yes, it's right.
Oh, okay. But then what's the data point here? And you have a green stuff with a vertical arrow bar. Are they also YSO?
Yes, they are calculated from YSO.
Okay, so I see. So this YSO identification is from previous paper, and you want to identify, you want to develop a new model, hopefully improve the YSO identification. Then
yes,
you can remake this physics plot. But how to determine you are doing better? What's the metric?
We may make a computer metric between the catalog we find and the catalog the previous paper find, and then see what the difference.
Okay. All right. Okay, thank you.
Okay, thanks. So if no further questions or comments, I think we're done with the presentations today.
Then maybe I can share, because I'm waiting for if anyone has any physics question. If not, then I do have a couple of editorial comments to this slide.
Mm-hmm.
It's important that when you prepare a presentation, you need to run a grammar checker, yeah, or the spell checker, yeah. There are several mistakes of the spelling in this slide. It's important make some efforts try to improve this. Yeah. This is my first comment, and my second comment is that your reference is very unusual style. So it's good that you can follow the standard notation to cite the reference. So you should cite the author and the title of the article, and then the source of the article. All right?
Okay.
Yeah, and I think the rest of the talk, most of group following that standard style, but you didn't. So it'd be nice you can fix the style of your reference for your final presentation.
Okay.
I have no more comments.
Okay, thanks.
Okay.
So I think today we still need to do the usual sign off by summarizing or reporting your progress for the week through Kaggle Notebook. So maybe TS can confirm, right? Is that still the plan for the week?
Yeah, yes. So
okay.
Yeah, as next week you just create a or copy and edit the new notebook to keep going your project.
Yeah, and next week will be the final presentation, and the following week you'll have to submit your written final report to eLearn. So if you check the eLearn website of this course, I have already set up the submission area for your final report. So please make sure you take note of the deadline of the final report. All right, so I think we're done for today. And so, Sujay, you want to add anything?
Yeah, so next week, every group need to present your final result. And I noticed that many of you propose a multiple machine learning study. And my suggestion is that you should just focus on one of them. So then you can present the full story. It's more important to present your work clearly, but not speed up and then put a lot of materials. The ideal presentation is that to show a minimal number of results, but you can go through them, make them clear to everyone. So you don't have to really put too much material, then you have no chance to go through them in detail. That's not the goal, okay? So I would suggest just focus on one proposal, get it through, and then present it clearly and explain every single plot. You need to explain what's the y-axis, x-axis, what did you observe in the plot, what did you learn from this plot. This is more important, all right? So next week, every group need to give a final presentation. And Jennifer and I will make it clear to everyone the metric of the final presentation. So then you will know how to prepare it and get your grades. And the written report in the end, 2 weeks from now, it's PIL style. That is, it's just 4 pages. And you need to follow the PIL template. It's part of grading. If you don't follow the style, and you will not get the good grade. And the written report is a single person report. That means each of you need to write your own. Of course, you will share your result with your teammate, but the writing itself is each one's effort. All right, that's it.
Thanks, Sujay. I think that's very important to note for the final presentations and reports. All right, so thanks everyone for participating in the presentation today, and we'll close the meeting.